ladies and gentlemen. We're going to do 5.6 today. We're going to be talking about our inverse trig functions. Our objectives are that we're going to review our inverse trig functions, which means we're going to be talking about restricted domains, solving trig equations, finding angles, and then we're going to take derivatives, which means you have some formulas to memorize because these just aren't necessarily intuitive formulas. All right. So as we get started, I want to go back and do a pre-calc trig review. And I'm recording in a new location. It sounds a little bit like I'm in a well. I'm just in my husband's office. So there you go. All right. So if we talk about the graph of y is equal to the sine of x, remember that it looks like this, with this being 2 pi. This guy is pi. I'm just going to do pi over 2, and then if I went this way, this would be a negative pi over 2. Remember that sine oscillates between a 1 and a negative 1. Alrighty, so if I wanted to take the inverse of the sine of x, I would do a horizontal line test. Well, if you'll notice, it fails the horizontal line test unless I restrict the domain. And I'm going to restrict the domain from a negative pi over 2 to pi over 2 so that I can actually take an inverse. Because as we've seen from the regular graph, I can't take an inverse because the function fails the horizontal line test. So what that means then, if I want to have y is equal to the arc sine of x, and remember that can also be written as the arc sine of x, you can write it that way. Okay. So if I want to find that, I'm going to restrict the domain of the sine function from a negative pi over 2 to pi over 2. So that means that the domain of sine, I guess I should have switched colors, would be from a negative pi over 2 to pi over 2, and the range would be from a negative 1 to 1. Okay, we'll just confuse everybody, and I'll just do the next part in blue. But if I go to the inverse function, which would be the inverse of sine, or the arc sine, remember that my domain and range switch places, which means that for arc sine, the domain is going to be from a negative 1 to 1, endpoints included, and then the range would be from a negative pi over 2 to pi over 2. And if you think about your unit circle, that means that for the inverse of sine or arc sine, your angles are limited to quadrants 1 and 4. I can't go all of the way around, but I can only do this positive rotation and this negative rotation. And one of these days it'll be nice if I can see if I can figure out how to get rid of some of these shadows. All right, so let's talk about our other trig inverse functions. So if we start with, we've already done sine, so remember that you need to know that arc sine is limited to the first and the fourth quadrants because of the way that we restricted the domain, and an inverse flip-flops the domain and range of the original function. So instead of doing that whole process for the rest of them, I'm just going to list that information. All right, so if we go to our arc cosine, so y is equal to the arc cosine of x, it's going to have, again, the same restricted domain. So for arc cosine, the domain is going to be from a negative 1 to 1. The range is going to be from 0 to pi. And if you think about that on your graph, here's 0, here's pi. That means that the inverse of cosine is restricted to the first and the second quadrant. And also remember that, just as a reminder, if I am seeing this, that says in words, find the angle x whose cosine ratio, I'm going to put a theta right there, is x. Okay, so that means that in this particular case, you're going to be given the ratio, and you're going to try to find the angle that has that same cosine ratio. All right, it seems like my outside boundaries are a little bit furry. That's better. Okay, So then if I go to my y is equal to the arc tangent of x, and remember that's the same thing as the inverse tangent of x. We can see it either direction. Then the domain for tangent is going to be all real numbers, and the range is going to be a negative pi over 2 to pi over 2. And again, if I'm thinking about my unit circle, that means that inverse tangent is limited to the first and fourth quadrants. And then we're going to go in and do our other 6 trig functions because they are all based off of the first 3. So my arc cotangent is going to have a range, sorry, I did this one backwards, from 0 to pi. So again, that's going to be quadrants 1 and 2. And then the domain of this guy is going to be all real numbers. Okay? If I do arc secant, then the domain is a little bit entertaining. It's the absolute value is greater than or equal to 1. I'll explain that in just a sec. And then the range is from 0 to pi. Alrighty? Which means this one again, but this one has an additional caveat that y isn't equal to pi over 2. And if you'll remember, secant is the reciprocal of cosine. So if I were to sketch my cosine graph, give it a couple of iterations, and then I superimposed secant on the top of it, remember that I'm going to have asymptotes at the zeros, and it's going to look like that, right? That's kind of cool. Alrighty, so there's the other half of his curve, and then that would be the top of his curve and the bottom of his curve. Alrighty, so that's why I can't have y equal pi over 2 because the world would explode. And then my last one would be my arc cosecant. The domain, oh sorry, I said I'd explain this. So notice that on these, my y values start at 1 and go up. So then when I rearrange my inverse, there we go, that was tough. When I do the inverse, the domain and range of the original switched places, which is why the domain is x, the absolute value of x is greater than or equal to 1. Because notice I had a negative 1 and a positive 1, so that's why this has this particular domain. So then the same thing would happen for cosecant because the graph looks virtually the same. It has different vertical asymptotes. And remember, if secant is the reciprocal of cosine, and if cosine is x over r, then that means secant is r over x. It means that the x's can't be 0, right? And that would happen where I had some pi over 2's. Okay, so the range for this guy is going to be the same as sine. So it's going to be pi over 2, negative pi over 2 to positive pi over 2. And the same thing, I have an additional caveat that y can't be equal to 0 because the world would explode. All right, so now let's just do a couple of examples. We're still kind of in the trig pre-calc world as we move through our material. So let's do some evaluating. First example, you're going to have the arc sine of a negative 1/2. And remember, if you needed to say that problem in words, what it would be was find the angle whose sine ratio is a negative 1/2. Well, the easiest way to do this is just to think about your unit circle. So remember that arc sine is limited to the first and the fourth quadrants. Sine is negative in the fourth quadrant. Sine is a y over r, which means this is a radical 3. This is 1, so that means that my x or theta, whichever you want to call it, is going to be equal to a negative pi over 6. So that was pretty easy. All right, let's do one with cosine. So let's have the arc cosine of a negative radical 3 over 2. So again, that says find the angle whose cosine ratio is a negative radical 3 over 2. And again, I just do it from my little unit circle. Cosine is limited to this quadrant and this quadrant. Cosine is negative in the second quadrant. This is a negative radical 3. This is 1. This is 2. This is going to be all the way to here. All the way to the x-axis is pi. So back up pi over 6. So my x or theta, whichever you want to call it, is going to be 5 pi over 6. Alrighty? And then, of course, we don't want to forget tangent, so let's do one with our arctangent. So the arctangent of radical 3. And again, the process is exactly the same as the other two. I'm going to go back to my unit circle. Arctangent is limited to the first and the fourth. Those are little tick marks, by the way, in case you wonder what I'm doing. Tangent is positive in the first quadrant. Tangent is y over x, and then that means that this is 2. So then my x, or theta, whichever you feel possessed to use, is going to be pi over 3 because it's a 60-degree angle. All right, let me change pens because people like to see me use different colored pens because it makes math so exciting. So I'm going to do some more evaluating. Oops, I'm going to evaluate, sorry. The first one would be an application of a handy-dandy little situation. So let's say I'm given that particular information. Well, it looks a little bit gruesome, but I could take the tangent of both sides, because remember, as long as I do the same thing to both sides, play nice with everybody, then it doesn't matter what I do to an equation. Well, this handy-dandy little situation removes the inverse tangent and would leave me at 2x minus 3. But here's the stipulation. If I want to do or invoke, let me circle this in a different color, if I want to invoke that process, this angle has to be within the restricted domain of the particular arc trig function, right? So arctangent is limited to the first and the fourth quadrants. Pi over 4 fits within that restricted domain, which is why I can pull off this process. So now if I do this, it's actually pretty easy. Remember that the tangent of pi over 4 is a 45. That means both of his legs are the same. So that means that this is equal to 1, and I get 2x is equal to 4, x is equal to 2. And then I'm done with that particular problem. So it didn't turn out to be as yucky as it looked. The only caveat that you have to remember is if I'm going to take the tangent of both sides of the equation, then this angle has to fall within the restricted domain of your arc-trig ratio. All right, so for my next example, all right, this time we're going to be given a slightly unique situation. We're going to be given y is equal to the arc secant of radical 5 over 2, and I want to find the tangent of y. Well, that looks a little bit weird, but it's actually not as bad as it looks, because basically all I'm going to do is take the tangent of both sides. So I'm going to write the tangent of y is equal to the tangent of the arc secant of radical 5 over 2. Oops, I forgot that parentheses. So if you remember in pre-calc, we talked about this is a composition. And when I do a composition, I'm always going to start on the inside, and I'm going to work my way out, okay? The inside says find the angle whose secant ratio is radical 5 over 2. So let's manage this part first, and I'm going to do that by drawing a triangle. So secant is the reciprocal of cosine. Cosine is x over r, which means secant is r over x, right? So then cosine is restricted, and arcsecant is restricted to the same domain as cosine, so that makes it easier on our poor little pea brains. So cosine is positive in the first quadrant, which means that this is, so secant is the radius, so this is radical 5 over x, this is 2. And if I do my Pythagorean theorem, 2 squared plus y squared is equal to 5, because radical 5 squared is 5, then I get y squared is equal to 5 minus 4, which is 1, so y is 1, so that little guy is 1. So now what this says If we rewrote it a different way, that says that the tangent of y is equal to the tangent of the angle that we just found, okay? Because I don't know what the value of that angle is, I kind of don't care, because now I'm going to take the tangent of that angle. It's the same angle. Tangent's y over x, so it's just going to be 1/2. And then we're done, because you were asked to find the tangent of y. I did, and it's equal to 1/2. So we're actually done with that part of the process. All right. The next thing that we're going to do is go back and remember, holy cow, look at that, just magically appeared, the derivative formulas for our trig functions. And the book wrote them in kind of an unusual manner, and there is kind of a pattern depending on how you try to remember them. Probably the grossest part of the derivatives of our trig functions is trying to remember the formulas. And so remember, you do need to commit these to memory. You definitely have to commit these 3 to memory, and then the bonus would be committing these additional 3. So if we look at the notation, and you can pause me and write these down, but if we look at the notation, remember that when I write it like this, I want the derivative with respect to x, and I have a u, so this is the derivative of u divided by the square root of 1 minus u squared. So you do have to pay attention to the notation. So whatever u is, you're going to take the derivative, that's going to be your numerator, and if you'll notice on all of the trig functions, the derivative of the u is going to be in every numerator. The trick is some of them are positive and some of them are negative. The other thing that you'll notice is, like if I look at the derivative of arc sine and the derivative of arc cosecant, notice that everything is backwards, which is kind of cool. I went from positive to negative. I went from 1 minus u squared to u squared minus 1, and then I throw in an absolute value. So whatever you need to do to remember those particular formulas is awesome. And yes, of course, in my room, they will always be posted. All right. Because we now know how to take the derivatives, and I'll do a couple of examples for us, but because I know how to do a derivative, that means that I also know all of these other things. I could maximize or minimize a function. I could do the first derivative test, and remember that would show me my extrema, and it would also show me my intervals of increasing and decreasing. I could also do my second derivative test, and remember that that's going to show me my concavity, or my intervals of concavity, and my inflection points. So because we know how to do a derivative, that also means that we know how to use that derivative either in any of these 3 different applications. So the assumption is, since you know how to do derivatives, you also know how to do these 3 things. All right, so let's do a couple of examples just to kind of refresh our brains. So if I wanted to take the derivative of the arc sine of 2x, then this is 2 over, because the derivative of 2x is 2, and then it's going to be 1 minus the u quantity squared, so then I just rewrite this as 2 over 1 minus 4x squared. And remember not to make those silly mistakes by remembering to square everything on the inside. Well, that was pretty easy. In our next example, let's do the derivative of the arc sine of the square root of x. Okay? So remember that the numerator is the derivative of the u, so my numerator is going to be 1/2 times x to the negative 1/2, and then I'm going to put that over the square root of 1 minus the square root of x, which is my u quantity squared. Well, if I simplify this, this is going to be 1 over 2 times the square root of x over the square root of 1 minus x, And then because this is over 1, I can multiply by the reciprocal. So this is 1 over 2 times the square root of x times the square root of 1 minus x. And now because I have two square roots, I can actually meld or bring the two radicals together. So I'm going to say the derivative, dx, of the arc sine of x is 1 over 2 times the square root of x minus x squared. So that wasn't so horrible. I have one more example for it, which is kind of entertaining, and we're going to do a little bit more algebra. Yay, algebra. So this is y is equal to the arc sine of x plus x times 1 minus x squared. That's going to be your given information, and I want to find y prime. So let's talk about the things that you have to notice. You're going to have to take the derivative of an arc trig, and then I have a derivative of a product. Okay, I also have the derivative of a chain. All right, so let's get started. So my y prime, the derivative of arc sine is the derivative of u, which is 1, over, and then the square root of 1 minus x squared. So he's done. Nothing to really simplify. This is the product rule, so it's going to be plus x times the derivative of the secant, which is 1 half, times 1 minus x squared to the negative 1 half times the derivative of the inside, negative 2x, plus the second thing, 1 minus x squared, times the derivative of the first. Alrighty? Okay. Let's see if I turn this guy off if the shadow will be any better. Maybe. I still have a shadow. It's all good. All right. So then I probably want to clean that mess up a little bit. So that 2 is going to go away, but it's going to leave a negative. So I'm going to have y prime. I actually like it better with that light on. I think it's a little bit brighter. Pardon me while I experiment. Maybe if I turn him a little bit. So I'm going to have 1 over the square root of 1 minus x squared. And then I have a negative x times x. So I'm going to put plus a negative x squared over the square root of 1 minus x squared. And then I'm going to have plus 1 minus x squared. Well, the goal would be to put some of this stuff together. So I'm going to write y prime is equal to 1 minus x squared over 1 minus x squared, because those two guys have the same denominator. And then I'm going to do plus, and then 1 minus x squared. I want to put these two guys together, so I'm going to multiply by the lowest common denominator, which is kind of boring because it's only one thing. Okay, so if I do that, I'm going to get 1 minus x squared plus 1 minus x squared over the square root of 1 minus x squared. Okay, so just to kind of simplify things a little bit, I'm going to get y prime is equal to 2 minus 2x squared over the square root of 1 minus x squared. I'm going to factor out the 2 and put it like this. And his power is 2 over 2. And then I have 1 minus x squared in the denominator, and his power is a half. So now remember that 2 minus 1 is 1, so this is just going to be 2 times 1 minus x squared to the 1. So the derivative of y prime actually simplifies just to be that. And we're done. That's it for today. I will see you tomorrow.